This is lesson 4.3, molecular shapes. So VSEPR theory, which stands for valence shell electron pair repulsion, says that electron pairs found in the outer energy level, or valence shells of atoms, repel each other, and so they try to get as far apart as possible, and this determines the shape of the molecule. So there's a few rules for VSEPR. The first is that there's repulsion not only between bonding pairs of electrons, but also between non-bonding pairs. Double and triple bonded pairs behave as a single unit. The total number of substituents around the central atom determines the shape. The shape is also determined by the angles between the bonded atoms. And non-bonding pairs of electrons have a higher concentration of charge, and so repel each other more than bonded pairs of electrons. So in order, lone pair repulsion is stronger than lone pair bonding pair repulsion, which is stronger than bonding pair repulsion. So linear molecules are formed when you have two substituents and they're placed at 180 degrees apart to form a linear molecule, for example in BeCl2. Planar triangular has three substituents and they're positioned at 120 degrees apart. If one of those substituents is a lone pair, the shape is bent. Tetrahedral shape is from four substituents. They're bonded at 109.5 degrees apart, and if one substituent is a non-bonding pair, you have trigonal bipyramidal shape, and if two are non-bonding pairs, you have bent shape. So remember that molecular polarity is not the same as bond polarity. Polar bonds do not always mean polar molecules. Polarity depends on not only the polar bonds, but the way the polar bonds are oriented, or the shape of the molecule. If the polar bonds cancel out, meaning that their dipoles point away from each other, the molecule is nonpolar. If the polar bonds do not cancel out, leading to one end of the molecule being negative and the other positive, you have a polar molecule. Giant molecular structures, or macromolecules, occur when you have networks of covalent bonds that form giant crystalline structures. So all of the atoms are linked by covalent bonds. Carbon is one of those atoms that forms macromolecules, and there's different types of carbon that we call allotropes, which are different forms of an element in the same physical state with different bonding. And so there's three different types of carbon that are all solid, that all have different properties that you need to know about. The first is graphite. Graphite is sp2 hybridized, and it's made of sheets of hexagons of carbons. They're in parallel layers, and the bond angles are 120 degrees because the carbon is trigonal planar in each case. The layers are held together by van der Waals forces. And if you look, the density of graphite is 2.26 grams per cubic centimeter, and it conducts electricity, and we use it in lubricants and pencils, and here's a picture of what graphite looks like. Another form of solid carbon is diamond. Diamond is sp3 hybridized. You can see here that diamond is tetrahedral in shape, so all of the carbons are tetrahedral, whereas in graphite they were trigonal planar. The bond angles therefore are 109.5 degrees Celsius, and diamond is the hardest known natural substance, very different than graphite. The density of diamond is much greater, 3.51 grams per cubic centimeter. It does not conduct electricity. It's very lustrous, where graphite is very dull. And we use diamonds in jewelry, tools, and machines for cutting. The last type of allotrope of carbon that you need to know about is called Buckminster fullerene, which is carbon-60. Sometimes we call it buckyballs. And here carbon is also sp2 hybridized. It's a sphere of 60 carbon atoms, 12 pentagons, you can see here the pentagon, and 20 hexagons. It looks an awful lot like a soccer ball. It's a closed spherical cage, and its density is much lower than either graphite or diamond. It's only 1.72 grams per centimeter cubed. It's a semiconductor, and we use it with potassium to make a superconducting material. It's also used in nanotubes, catalysts, and lubricants, and you can see it looks much different than both graphite and diamond. Another element that forms macromolecules is silicon, and silicon dioxide is a macromolecular structure. So silicon, like carbon, has 4 valence electrons and forms giant lattices. Silicon dioxide, which is silica or quartz, is a giant covalent structure, and it has a very high melting point and does not conduct. It's the main component of sand and glass.